into this SPI serial port today and start on trying to understand how we get information from the red board, from our launch pad, the 28379D processor, over to these additional peripherals. So the idea, what I want you to think about when you think about these SPI chips, you know, we've got a load of things on the F28379D. You know, we've got all these PWMs, PWM1, PWM2 we've been playing with, 9, 12, right? We've been playing with all these. We've got, you know, ADCs, a bunch of ADCs. We even have some DACs. So we've been playing with those. So all these peripherals that TI's been able to put inside the chip, okay, inside the F28379D. But there's still some things that we may want to add outside of the chip. And that's where SPI, well, UART works too, but a lot of chips that you want to talk to that add, what are we going to add? We're going to add in homework an IMU, right? Or gyro, a acceleron, 3 axes of acceleration, all this kind of stuff. What else is there to add? I'm going to show you a number of things. We have inside the F28379D, we have the EQEPs, which is our quadrature encoders. But there's only 3 of them, right? And we're using all of them already. We've got our encoder for the left wheel, we have the encoder for the right wheel, and we have that third encoder, don't we, with our knob, right, we've been using. What if you need some more? Like, let's say you wanted to use this chip and control a 6-link robot arm, right? There's only 3 optical encoders. Each of those joints usually have an optical encoder on, telling you what the angle of the linkage is. So you have to have a way to add some more optical encoders, all right? And that would be something you communicate with a chip, and as we're going to talk about a kind of chip that does that today, actually. That we would use the SPI serial port to communicate that and get that information from another sensor, an angle sensor, or whatever else we need. Okay, so it's great. You know, TI's put a lot of good stuff inside this chip, but we may need to add more things. Okay, so that's why they give us the SPI peripheral, to get information out of the chip to other devices, okay? To talk to other devices. Now there's another protocol. I've decided, if you're interested in the protocol I2C, make sure to talk to me and we can make some kind of project for you to work on that. I've got lectures on I2C and all that kind of stuff. Just looking at the schedule for this year, I've taken I2C. We're not going to dive into I2C, at least in homeworks and stuff like that. But if that's something, you know, maybe you've heard of that playing around with your Arduino or whatever you've been doing in the past, and that's something you're interested in, make sure to talk to me about that, because we definitely have ways to teach you that too if you want. But anyway, we're going to focus on the SPI, Serial Peripheral Interface is what that stands for. And it's for short wires. You're usually not going to see someone SPI from one device to another device over meters of wire. Okay? We're usually talking centimeters of wire. Okay? So in other words, a chip and another chip sitting on the same circuit board. Or maybe going up, you know how the headers are on, our headers, our black headers on the red board, maybe going from one board down through headers to another board, right? That would be the distance you'd be traveling with these wires. Yeah, there is a protocol that's very similar to SPI called SSI. I forget what that actually stands for, but that protocol actually has transceivers on both ends, and so it can send extra length of wire. So anyway, it's similar to SPI, but anyway. So there's options if you need to transmit over longer wires. Okay, so that's what we've got. Now, we've got to remember, right, we've got this handout. I don't think I gave it to you. I didn't hand it out, but it's here at the lecture notes that I want you guys to to reference, especially when we're talking about the different modes of, where is it at? The different modes of the SPI. Okay, so again, these aren't, you have to zoom in on these to see. Let's see, can I open in desktop app? Let's see, there we go. That's a little better. Those texts, the ones and zeros are so tiny guys, you have to zoom in. But I give you a plot of, there's 4 modes, remember that? So the clock. So polarity 0, phase 0. What that means is the clock is normally low, and in this case, with this mode, we're reading data on the low going edge of the clock. Okay? So normally low, reading data on the low going edge. And then we go to mode 0, 1, or just mode 1. It's all the same except for the clock is normally low, but we're reading data on the rising edge. Okay? And I'm going to give you some examples. We're going to go through some data sheets and see that different chips use different modes. Then there's the mode 2, or 1, 0, where polarity is 1, meaning the clock is normally high, and we're reading data on the rising edge. Okay, that's of the clock. And then finally, mode 3, 1, 1, is again clock normally high, reading data on the falling edge of the clock. Again, I would have loved for them to just pick one of these modes and just use it always, but the designers chose not to do that. So we have to deal with these 4 modes. And then this chart down here, again in this handout, or you'll see this in the reference guide, this talks about all 4 of those modes. Oops, what did I do? We've got all 4 of those modes right here. Okay. Before we actually go look at data sheets, again, let's make our drawing of how this works. And I really, when you're thinking about SPI, you're confused, I think it'll be the best for you to draw a picture. At least when you come to me with the question, what do? I get out my notepad and we're going to draw a picture of how this is all wired up and everything. I think it'll help you. What I mean by that is, let's just do it. So we've got, again, our breadboard and the chip on the breadboard, right? F28379D. And I'm going to make it bigger so we got more room here to work with it. Inside that chip is the SPI peripheral. And there's actually SPI A, B, and C. We're going to be working with this homework, SPI B. And then actually we're going to take this code, and in Lab 6 we're going to merge this SPI code into our Lab 6 code so that we can use the IMU on the robot also. Okay, and then if you remember, the pins of the SPI are master out, slave in. And again, sometimes you see that labeled SIMO. They're the same thing, right? They move the letters around a little bit. So this master out pin, the master is always driving this. The slave never has control over the master out pin, which kind of makes sense. So this is the pin that the slave's going to read in data. And then we've got the master in, slave out, and of course, sometimes that's called SOMI, depending on which data sheet you look at. Oops, wrong direction. That is an input. So the slave always has control over this pin. So that's an input pin because it's coming into the master, right? So we have this idea of master. In our case, the master is always going to be our 28,000 chip, okay? And the slaves are going to be all the devices we're talking to, okay? Well, in your case, in the homework, you're just talking to one device, but there could be more. Then we have the S clock. Sometimes they just label that SCK, you'd see it. Sometimes it's just called clock. Anyway, you can figure that out. That's always, this is another pin, this is always driven by the master. So the master must produce the clock. Okay? And finally, a slave select or chip select, sometimes it's called, right? That bar over the top, most of the time, chip select is active low. That means to turn on a device, you have to pull the I/O line low, okay? And then that turns on the chip, and then the chip will communicate with you. If you don't have that pin low, the chip thinks you're talking to someone else. It'll see the lines going high and low, right? The clock lines and all that kind of stuff, but it'll ignore it because you haven't selected it. Okay? And most of the time, definitely here, you only select one chip at a time. And again, the slave select is controlled by the master. All right. Well, how can we wire this up again? And then this is also where I want you to, kind of draw a picture of the devices that you're communicating with, because this makes you remember that you've got to write to the serial port to get information out to these chips. Okay, and I'll hopefully make that a little more clear here in just a second too. But these devices, like we're going to talk today about this LS7366 chip. I'll explain that guy. It's got a master in, slave out. It's got a master out, slave in. It's got an S clock. And it's got a slave select. Okay? Then your homework, you're going to be really dealing with the MPU 9250, our IMU chip. It's got a master in, slave out, slave in, an S clock, and a slave select. Okay. Finally, let's just do another one. I've just been playing with this chip lately. The MCP. We don't even need to know what it is, but we won't get that detailed. But it has the same pins. Okay, master out, slave in, S clock, and chip select, slave select. Okay. And so how do we wire this up? So, right, we did this last time. So the master out is going to go to all these guys' master out pins. So they're wired together, right? And then the master ins go to all the master in pins, daisy chained from one to the other. And finally the clocks. They're all daisy chained too. If you can, kind of sloppy there. See what I'm doing? Okay. Finally, the unique signal. So those are all the same signals going out to those chips. The unique signals are these slave selects. So we're going to find, and some people have started into homework, question 3 on the next homework. We are going to find that GPIO 66, we're using that to select the MPU 9250. Okay? We're also going to have another device on the, let me think, I'm pretty sure it's GPIO 29, okay? That selects one of these other devices. And then we can pick whatever, this isn't actually on our board, but let's say GPIO 52 is connected to this guy, right? Okay. So there are multiples of these slave selects, in other words. So yes, there's some pin. This one happens to be GPIO 66, let's say. So we're labeling this a slave select or a chip select. Now, there is no functionality of pin 66 to be, how we look at the pin mux table, right? And it has all these properties of what it can be, a PWM line, a serial port line, or whatever, right? Well, to make it a chip select for us, it's just a GPIO. So we will set up GPIO 66 as GPIO 66. So option 0, right? You know what I'm talking about with the pin mux? Got that? Good. And so you think of GPIO 66 as a pin just like turning on and off an LED like you've already done, right? By setting, using the G, in this case it would be what? GPC set, right? .bit.GPIO 66. And if you want to set that pin, you would set the set register, that bit, to 1, wouldn't you? And if you want to clear that pin, you would do GPC clear, right? .bit.GPIO 66 equals 1. And that will clear that IO pin. Agreed? That's stuff we've been doing all along, haven't we? So that's how we play with the 66. And so you'll find that we have to put these guys, these are serial port pins. So let's go look at it actually. Let's go look at the pin mux guide. So to do this, you'll be setting this up. Come on, go quicker. Is it going? Are we down? No? Oh, can't reach site. Interesting. Well, is my network down? Connect. All right. Well, I don't think I have it on my computer. What do I have? Just went down? Okay. So, well, if we go to the pin mux guide, let's see if I have it in one of my folders here. Lectures, one of my early lectures maybe. The peripherals, not looking good. Okay, well, you have to take my faith. So we go look at it. GPI, we go find in the table GPIO 63. That's what I'm forgetting. I don't remember what mode it is. I don't remember what number it is. Let's say it was 5. I don't know. I don't remember. It could be any of those mux modes, right? The mux numbers. Let's say it was 5. So you would, obviously, in your code, set up GPIO. This is 60. Again, I don't remember. One of these is 63. One of these is 64. One of these is 65. Just happens to be. And we'd be setting up these 3 pins as serial port pins. Okay? Through the mux. Muxing those to say option 5. This guy, though, is just a GPIO. 66 would stay a GPIO. So mux mode 0. Just like we've been setting. Okay, so what does that mean? Once you've set those guys up, those 3 pins as serial port pins, yes, they were GPIO 63, 64, 65, but now you've set them up as serial port pins, so you cannot manually move them high or low. The serial port has total control over those pins. That's what I'm trying to make clear here, right? And so when you want to send data out on those serial pins, you've got to write data to the register, and we're going to get to that too, the SPI transmit buffer. That's your only way to get data out of this serial port, is by writing data to that register right there. And once you write data to the transmit buffer, it starts shifting out the bits one at a time, every clock, right? So the serial port starts producing that clock, and also starts shifting out your bits. Okay, one at a time. 1 bit at a time. That's what serial does, right? Serial is sending 1 bit at a time across the wire, isn't it? And in the same way, remember, the mantra we're always going to talk about when we talk about SPI is for the SPI to read information, you must write something out. You have to. There is no way for the SPI to receive information without you writing something. Okay? So that's where you're going to see in the data sheet today that I go through, you're going to see that there's times when you have to just send anything, or garbage, or whatever you want to call it. And most of the time when I see in the data sheet that you have to send something, I always send 0, because that makes like a sense of something to do, right? But you can send anything in those times. And I'll explain when we get to that in the data sheet. And so, when you write something to transmit buff, after you've transmitted out 8 bits or 16 bits, whatever you've decided to do, you will have that many bits sitting in the register SPI receive buffer, RX buff. And so to get information from the SPI, you need to read this register. RX buff. These are your only 2 windows into the serial port. Yes, there are some initialization registers that say what baud rate to run at, and to reset the FIFO and all this kind of stuff. We'll talk about this thing called the FIFO. But that's only done once in main. Yeah, we got to start it all. We always have to do initializations. But after we're done with those initializations, the only two registers you talk to are transmit buff and receive buff. Okay? I guess the only reason you would talk to some of those setup registers, as we're going to see in just a second, let's say you have two chips on your bus. One of them uses mode 0 and another one uses mode 2, right, of the high and lows of the clock. That would be a case where you would have to write to the setup registers again to switch between those modes before you wrote to it. Does that kind of make some sense? Let's think about that actually. Okay, so let's look at some devices and look at some of these modes. So I've got a bunch of data sheets here of some chips that I've worked with in the past or currently interested in. And let's go look at this, which would be a good one. Shoot, we'll go ahead and start with this one. Yeah, we'll start with the LS73. We're going to talk about this chip a little bit today. So again, now it gets a little confusing, and so I try to help you out with this when we're doing a new chip. But to find the timing diagrams, you just kind of comb through the device, and here is a pretty good looking timing diagram. Sometimes these are super confusing. This one's not too bad. So by looking at this device, to figure out what SPI mode we have to use, notice that the clock, right, they call it S clock, SCK, is low when we're not doing anything. It also remains low afterwards. Now, see, personally, if I was writing this for you as a homework assignment, I would leave this line longer to low. It's a little deceiving. What happens after that little bit time? But anyway, I know that it's supposed to be low continuing after that when you're not using it. So, right off the bat, you know that polarity of this is 0. Agreed? When it starts high, that's polarity 1. When it starts low, it's polarity 0. So now all you have to decide is what edge we're reading data on, and then you know if it's mode, what would it be, either 0 or 1 are the two possibilities of our modes. So let's remind ourselves about that mode again. So it's one of those two modes. Right here, which are these two right here, but I like personally, I mean it's up to you which diagram you like, it's one of these two up here. So again, we have, this is mode 0, 0, 0, clock, polarity 0, phase 0, and this is the other one, phase of which phase equals to 1. So we are reading data, right? This edge, see, look what happens with SPI. On this edge right here, we are taking in the value that's on the data lines, either master in or master out. Well, obviously, the master in is reading in data on that edge. Master out, then the slave is reading in information on that edge, right? So you got to think who's reading on the other one. But okay, and then notice that on the other edge, right, on the low going edge here, the data transitions to the new bit. So in other words, because the first most significant bit that we are reading in, this is master in, is a 1, the slave knows to transition to the new bit when the low going edge happens in this mode. And so it stays. But now, notice it didn't have to transition here because the next bit is also 0. But when it transitions to this bit, which is this most significant, then down, 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 the fourth from the most significant or whatever, we have a transition to it on the low going edge of that clock before, and then we can read on the rising edge. Okay, anyway, so now what we got to do is we got to go to the data sheet. Which one was it? Right here. And what edge are we reading data on here? You kind of have to. I mean, we can even probably zoom in, I guess, a little bit. So look here. Look how the data, when we talk to this, and we're going to try to understand this a little bit today, when we write to this certain register, bit 7, or the most significant bit, needs to be high. And then we have a 0, 0, 1, 0 is what we're sending, right? Well, this data sheet is showing us, look, we are reading data on the rising edge. Does that make sense? Because it's in the middle of where this bit's been set up that we want to read. We are transitioning, see how it goes from 1 to 0 right here? We're transitioning on the low going edge. and then reading 0, and then reading 0, and then again transitioning to this 1 on the low going edge. Okay, so if we go back to this, so we're reading data on the rising edge. What mode is that? See right here, it's this one, isn't it? Because mode 0, we were reading data on the low going edge, weren't we? So it is mode 1 for that chip. Kind of get what I'm doing there to figure that out? Okay, let's look at another data sheet. This one I think's got a funky. So we gotta have to, again, you just kind of comb through the data sheet to find these diagrams. Sometimes they're really confusing, but here's a pretty good one. So if we zoom in here, yeah, so to talk to this guy, what's polarity? Someone help me out. 1 now with this one, isn't it? So this chip wants the clock normally high. Now, look here. They, you know, each data sheet does it different. I like to draw my edge. They decided to draw their line from the bottom to the top at the transition edge. Do you see that? See, what this is saying in the data sheet, data bit 11, this is the data sheet. It doesn't know what data is coming back when it's actually running, right? And so what this says, by having it transition high or transition low, they're saying data bit 11 could be low or it could be high here. You see what, that's how they're determining that. And so what we're doing, the middle, we set it up, we move to the bit, and then we read that bit on the low going edge. Do you see that? And then, you know, transition to bit 9, and then read it on the low going edge. Okay, see how I'm getting there? All right, so for this guy, this chip, we would be in mode, we're reading data on the low going edge, so that would be mode down here in these two, normally high, reading data on the low going edge, so that is option 3, isn't it? Did I say that right? Low going edge? Yeah. Okay. So this would be the mode you use for that chip. Okay? And yes, if both those were both on your SPI bus, you would have to be switching modes before you talk to that other device. Okay? Switch before you run. Good. Okay. And so that's the idea. And then we can look at other chips. You know, let's not pound it in too much, but let's see. Our MPU 9250. You guys, I think I give you the mode, but here's one. Here's a diagram. It's polarity 0, isn't it? Reading data on the rising edge. So I believe that is mode 1. Let's go check. So reading data on the rising edge, transitioning data on the opposite edge. So that gives us mode 1, I believe, here. That's right, reading data on the rising edge right here. So that would be mode 1 for our MPU 9250. And then we can look at other devices, and you know, some are, I find most devices are mode 1, and then the next mode that I find devices are mode 3, that I've played with. But you obviously could find other ones. Okay, great. Now, that's fine and dandy. All right, great. So you've set up the mode now, Dan. How in the world, or what do we do to get data now across from the 28379D over, and let's specifically talk about it. We're not going to actually talk to this in homework or anything, but this is a good one to just kind of get an idea of what data do we have to send across to actually read the optical alert. So in other words, this chip, its goal is just to keep track of those counts of the optical encoder. Remember, we talked about that with the EQEPs. We've got these 2 square wave signals, and it's counting every time it sees a transition from high-low to low-high and all this kind of stuff, right, with those clock pulses. And so all it's doing is counting every time. And then we know the number of counts per 1 revolution of our optical encoder, right? So its full job is just to keep track of that count. So it's got an A and B channel, and that goes to our optical, and this is wired to our optical encoder sensor. Okay. Now, I mean, you can think of it. Remember the knob you have in your hand. Remember that long wire, right? That long wire is carrying 5-volt power, ground, and then this channel A and channel B. So let's imagine with this, we want to add a fourth wheel, right? That's the idea here. We'd only have 3 encoders inside the 28 chip, 28379D chip. So what if we had to add a fourth? Okay, that's the idea here. How would we talk to that? All right, so this is where we go back to having to dig through data sheets, okay, and understand what's going on with this thing. So if I go back to my PDFs, let's look at this data sheet now. Let's zoom back out a little bit. Okay. You know, and techniques for reading through a data sheet. Good question. What I always say is you read and you reread and you reread, because you'll read through it and you'll say, okay, I think this is how to do it. Or you'll read through it and you'll go out on the web and find some example code. That's a really good way to understand this chip. Find some people that have done code for this for something else. Then look at their code, reread the data sheet. You know, so you're just kind of going back and forth here to figure this all out. I'm not saying ever do I read the data sheet once and understand it all the way. Okay, so you guys would be doing the same if I gave you the task of working with this chip. All right, but the front page of a data sheet is always good to read through, because it gives you an overview usually of the whole device. Okay, but when we start getting down to the registers, so let's think about that. Here are some of these, well, that's the pins, sorry, that's the pins. That's always a good one to read through. But then we've got the different registers that we want to talk to on this device. We've got the status register. We've got this thing called the instruction register. And then we've got a MDR0, master something something. What does that stand for? The mode, that's right, it's got mode register 0. Okay, and then we've got this mode register 1. And what else? I think there's one more. Well, yeah, and then just the way they don't list it because it's just the count register. Okay, so we want to read the count. Remember, that's all this chip is doing, is keeping track of the number of counts the optical encoder is turned, right? So our job is to go and read that count. That's what we want to do with this chip. Okay, they do have this data transfer register and this, what is the OTR? But anyway, these are all just ways. So the idea is, if you wanted to, you know, there's always nice, if you want to, now I'm going to try to spit out. A lot of times in control of systems, especially if you're sampling really fast, it's nice to actually just go and latch your reading and then take your time to get that data pulled across SPI. That way you know all your feedback is being sampled, boom, at the same time. So anyway, that's why they give you this, the data transfer register, and I think something like the output transfer register, that's what you can latch. Anyway, so they give you a little bit of extra complication here. Let's not worry about those two registers. Let's just think about the counter register. But anyway, because we're going to just go read that. Okay, so how do we do that? Well, actually, they do give us an example down here in that timing diagram, yes. So they give you the bits right here for writing to the mode register 1. Okay, now, very confusing here. Let's try to decipher this. Okay, well, how many bits are going across? Well, in this case, we've got 16 bits going across to write to the mode register. But if you notice down here, if we want to read data, we are going to need to send 8 bits, and then read 8 bits and read another 8 bits. Okay? So what we're going to find, and we'll talk more about this with the MPU 9250, it actually works really well to send and receive 16 bits at a time with the MPU 9250 that you're going to be using in your homework, okay, and also in lab. But with this chip, it makes more sense to actually send and receive 8 bits. Okay? So there's a setting in the SPI, it's called, and you're going to be setting it up, called SPI char. The size of the character or the word or number of bits you want to send in a sense at a time. Think about in terms of how many bits at a time. And you can set SPI char to anywhere between 1 bit at a time, which I don't know when you would ever want to do that, that'd be silly, up to 16 bits transfers. Okay? Normally, most people will either decide SPI char is 8 bits or 16 bits. That's usually your choice there. Now, well, there probably are some devices out there that take less than that, and maybe you choose that. But for the most part, you'd choose SPI char to either be 8-bit chunks or 16-bit chunks. Okay, great. So let's look at this again. We want to write to this mode register. Okay, let's go look at the mode register. Mode register 1, right here. So here's our 8 bits. Now again, where is this located? That's really important. So you get this in your head. Come on, back to me. So let's draw this again. Let's blow this out. That we have the F28379D, and we've got our SPI. So we've got our master out, slave in. We've got our master in, slave out. We've got our S clock, and we've got our GPIO. I think we said 29 or whatever for our slave select. Okay, so that is connected to this LS7366 chip. Okay, and we've wired this over. It's master out, slave in. It's master in, slave out. It's S clock. I think they just call it SCK, and then it's slave select. Okay? This mode register that I'm talking about is sitting inside this chip. So the MDR1 that I'm looking at, it also has this thing called the MDR0. And then our most important one, it's got the count register, count or whatever, that is actually 32 bits. Okay? So 8, 8, 8, 8. Okay? So those are the kind of important things that are out there on that chip. We need to write to that, the mode registers, to get the chip going. Right? And when on power up, it's not counting anything. So you got to write to the mode register and say start counting. Okay? And then whenever every millisecond or whatever our sample rate is, we'll go out and read that count. Okay, so that's kind of the goal. And all these are sitting here. So what I see people do when they're thinking about SPI, they're thinking, okay, that means if Dan says there's a mode register out there, well then maybe there's something called, like we say GPIO, I don't know, they would put in class, they would say LS regs dot register MDR 0 dot bit equals, right, or something like that silly. There's no such thing as this. Why? These regs dot whatever, these are all registers on this chip, right? These registers we're talking about are sitting off the chip, off the 28379D, and inside the LS7366. The only way to get data into this register is over here to write to SPI B regs dot to write to it would be SPI TX buff equals. Okay, that's how we get information from the 28379 over to this device we're talking to. Okay, so keep that in mind. All right, great. So what do we have to do? Well, to do this mode register, come back to it, Dan, where are we at? Here we go. All right, what do we want to do here? So mode register 1, we want to set B0 and B1 equal to 0, 0. In other words, we want the count to be able to count up to 32 bits. I don't know, some other folks may want to use the other modes, just count up to 24 bits or just 16 or 8. I don't know where you would want to do that, but anyway, we want these 2 bits to be 0, 0. Okay? Do you agree with that? We'd like a 32-bit count. Then, what do we want to do? Do we want to disable counting or enable counting? Obviously, we want to enable counting. We need to set B2 equal to 0. And then not used. When I see something that's not used, I set it to 0. Okay? And these guys, okay, there's ways to, there's some flag inputs on this chip to tell it to a nice idea with these flags are like if you wanted to home a robot and you had a optical sensor, and then when it tripped that optical sensor, you zero the encoder. That's what these flags would be used for. We're not doing anything with the flags, so we would just ignore them. Let's see, no op, right? So we'd keep them as no operation, wouldn't we? Okay? So we need to write 0 out to this guy. Because I'm not 100% on this, but I think on power up, the bit 2 is by default 1. The counting is disabled. You need to talk to it and say, hey, start counting now. And you just do that once. You know, you're saying, turn on, start keeping track of where the encoder is, the angles of the linkage, or of our motors, of our wheels, and all that good stuff. Okay, so for this one, we're going to have to write out 0. What about mode register 0? Okay, so again, this is similar, isn't it? This looks a lot similar to what we've been doing with the registers on the 28379D, agreed? I kind of give you those question marks, and you guys go to the registers and you figure out what bit's 1 and which bit's 0. Okay? Same thing, but there's just a different transfer method to get that over to your SPI chip. Okay, so for this guy, bit 0. You remember how I told you with the A and B channels, the number of slits of that optical encoder, the slit gives us 1 full square wave of the A channel. And then the B channel is 90 degrees out of phase of that. And because of that, we can turn 1 slit into 4 counts. All right? That's what this 4 times mode is. The only reason I think you would use non-4 times mode if your encoder is going really fast. This chip can handle up to certain rates at each of those modes. We don't have to worry about that. We don't go that fast. So we want this to be mode times 4. Okay, so we'd set this to 1, 1. This free running, single cycle, yeah, we just wanted to keep on running forever. So free running, 0, 0. Disable index. This again, these are those flags that I was talking about. And we're going to just disable the index. We're not using that. 0, 0. Let's see, whatever. The negative index pulse, yeah. This is for, again, a flag, so we're not going to worry about that. It doesn't matter. We'll just pick one. We'll say negative index input. And then finally, this filter clock. There's a way to filter out certain glitches. You know, so what happens when these A-B channels run across long wires or right next to electric motors and all this kind of stuff, there can get some interference on those wires, and this helps to filter out some of that interference. So I usually use the clock divide of 2 to make it filter a little bit better. So we want to set that guy to 1. Okay? All right, great. So what we need to send across, if you look here, if we go back to that timing diagram down here, we first have to send across 8 bits right here that say, hey, chip, hey, LS7366, I would like you to send the next 8 bits that I send to mode register 0. Or, hey, chip, I want to send a command such that, hey, the next 8 bits I send you, I want you to send it to mode register 1. Okay? Well, they do that a little cryptic, but anyway, that's the way data sheets are, so I want to show you how they chose to do that. And that's this thing called the instruction register. So we want to write to those chips, right? To those registers. So bits 6 and 7 of this register are 1, 0. Okay? What register do we want to write to? We, for example, want to write to mode register 0. Okay? And so that is these bits. So bit 3, so that'd be 1, 0, 0. And finally, the bottom 3 bits are don't cares. So we just set them to 0. Okay? So that is the number 88. Right? Do you agree with that? That's hex 88, those 4 bits. Now, so that's to write to mode register 0. To write to mode register 1, the difference is we still want to write, so that's still 1, 0. What do we want to write to? Mode register 1. So that's 0, 1, 0, and then 0, 0, 0. Okay? So that's hex 90. So when we run, that's to write to mode register 1. Remember, it was hex 88 to write to register mode register 0. So what would we do? All right. So to make this work now, we've got to, and let's go back to this. We've got to send 2 bytes to make this happen. So right here, right, we've got sending out that 88, for example. What is this? This is mode register 1. Here's our 1, 0, 0, 1, 0, 0, 0, 0. That's right. That's hex 9. This is hex 0. See what it's doing there? Okay, so we write that. And then what do we write here? The value we want in mode register 0. And what did we say? I think it was hex 83, right? Which was we want to send 1, 0, 0, 0, 0, 0, 1, 1. Because remember, this was the times 4. Okay? Oh, wait, that's mode register 1. Sorry, this was mode register 0. We were wanting to send all zeros, wasn't it? We just wanted to send all zeros just to start enable counting. But anyway, all right. Kind of clear a little bit? Okay, so that's what we're going to send. Now, how do we do that in code? So what we would say is the following. Let's go to Code Composer. Let's just think about how we would write that. So down in, say, an interrupt routine or up in main, somehow, let's do it in main, without interrupts at first. We would, in our code, have to first pull GPIO 29 low, okay, to chip select the chip. So we would say GPIO data regs. I'm not going to get everything here. Data regs. Oh my gosh. Dot. And then, oh, not data. Yeah, that's right. Data regs. Dot. And then it would be GPA clear dot bit dot GPIO 29 equals 1, right? That would enable the chip, wouldn't it? Then we will, for this chip, we will set it up in mode for sending 8 bits at a time. As I said, in your homework, we're going to be doing 16 bits at a time. So then what you would do is you would say GPIO data regs, SPI B regs dot, hold on just a second, we'll just finish this up. SPI transmit buff equals 1F equals, well, what did we say? We wanted to send first OX88. This is mode register 0. Okay? And then the next bit, right? This is telling the chip, hey, the next 8 bits that come, put these bits into mode register 0. So we got to send one more 8-bit value, and we found that was SPI B regs dot SPI TX buff equals OX, I think this was 83 for mode register 0. And then we would have to pull chip select back high. Well, we have to wait, actually. So actually here, we'll get to this next time. We have to wait until transmission done. And then we pull it back high, don't we? GPIO dataregs.gpaset.bit.gpio29, right? Equals 1. Okay? And then we would do something similar like that to talk to mode register 1. This was talking to mode register 0. But then we have to remember, last thing, because we sent something, we also received something. Now, looking at the data sheet, you'll see, what did we receive? This line like this, when it's like this, that means nothing, or garbage, or things that it doesn't matter. It's sent, we're getting it. Could be floating, could be any numbers. We did receive that though, so we have to read it off the FIFO, but we ignore what we read. Read it into, say, temp variables, and then just ignore them. Okay? Later on, we will see right here that there's a way to actually get real data from the chip, and then we'll use it. Okay, good. Let's go with that and see how that goes. Let's ask me questions as you keep on working on it, and we'll talk more about this on Monday.